Hello everyone. Today I will explain first shifting theorem. It is a famous theorem in Laplace transforms. This first shifting theorem, also known as first translation theorem. Let us see its statement. If L of f of t equal to f of t, then is the first bit. Laplace transform of e power minus at f of t equal to f of t minus t plus a. Second, Laplace transform of e power at f of t is equal to f of t minus a. For proving this theorem, first we should understand the definition of Laplace transform of f of t. Basically, L is an operator. We call it as Laplace operator. It transforms, it changes function of t into function of t. And its definition is L of f of t equal to integral 0 to infinity e power minus pt f of t dt. This integral represented by f of t, where p is parameter. Let it be equation 1. And in the theorem, given data is Laplace transform of f of t is equal to f of t. That is given. So let us start with given data. Given L of f of t is equal to f of t. Next, we should write definition of Laplace transform of f of t. Nothing but integral 0 to infinity e power minus pt f of t dt, which is denoted by f of t. Let us assume it as equation 1. Let us start to prove bit 1 and bit 2. First, we will go with bit 1. In bit 1, we have to prove Laplace transform of e power minus at f of t is equal to f of t plus a. For this, we should consider L of e power minus at f of t. We should compare this L of e power minus at f of t with L of f of t. And using equation 1, in place of f of t, we should write e power minus at f of t. So, right side becomes integral 0 to infinity e power minus pt as it is. And in place of f of t, we write e power minus at f of t dt. Next step, that equal to integral 0 to infinity. Here, e power minus pt, e power minus at, both are in multiplication and bases are equal. So we can add their powers. And in the powers, we can take minus t as common. Then we get integral 0 to infinity e power minus of t plus a of t, f of t dt as it is. In next step, integral 0 to infinity. This p plus a, let us assume it as u. Let us take. Then this value becomes e power minus ut. F of t dt remains same. Now observe again equation 1. In the equation 1, in the integral 0 to infinity e power minus pt f of t dt. Then the entire integral represented with f of t e power minus pt here, then f of t. Now what we obtained in the last different step, integral 0 to infinity e power minus ut f of t dt. Compare this equation, let it be 2, this 2 and 1, both you compare. Then in place of p, we have u. So, if we have p, then it is represented by f of p. Here we have u, so it is represented by f of p. And we assumed u as p plus a, so we replace u with p plus a. Then what we obtain finally, L of Laplace transform of e power minus at f of t equal to f of t plus a. That's our requirement. We reached it. Okay. Next, we'll prove bit 2. In bit 2 also, we do the same. We prove Laplace transform of e power at f of t equal to f of p minus u. For this, let us consider L of e power at f of t. And again, take help of equation 1. In equation 1, we have L of f of t. For it, formula is integral 0 to infinity e power minus pt f of t dt. Now, in the second bit, we have L of e power at f of t. So, in place of f of t, we have e power at f of t. So, in right side of equation 1, you just replace in place of f of t, e power at f of t. Then it becomes integral 0 to infinity e power minus pt into e to the power at f of t dt. Now, here also, inside the integral, e power minus pt, e power at both are in multiplication and bases are equal, so we can add their powers. Then it becomes integral minus 0 to infinity minus pt plus at. Let us take minus common, t common, then it becomes p minus a of t. F of t dt remains the same. Like previous bit, let us assume p minus a as a sum v. Then it becomes integral 0 to infinity e power minus v t f of t dt. What's the reason behind this step? We put just p minus a as sum v. Right. Now observe, let it be named as equation number 3. Now this third equation and this first equation, both you compare. Then you can understand. In place of e power minus pt of equation 1, in third equation we have e power minus vt. There p, here v. If there is p, then its value f of t. If here is v, so then its value becomes f of v. Finally, what is v? By our assumption, p minus u. So, with what we started, Laplace transform of e power at f of t. Finally, we reached its value as f of p minus u. That's our requirement we reach. Thank you.